having questions. Okay, so so for part one, I would like you guys to be able to export into a single file some kind of something that animates. And so I know some of you are struggling with getting Image Magic to work. I know a few students have got it to work, figured it out. And I know I've, on Piazza, where is, I did come across this installer from Cactus Lab, and apparently this does work, okay, but might require I don't know, just changing a few of the settings in or I don't know in the way we're exporting. But I don't have a Mac, so I haven't been able to figure out exactly how this needs to be done. And I was going to get one of the students to share how he got it to work, but we couldn't figure out how to hook up the the screen to his laptop. So maybe we can figure that out. As for part two, okay, it says pick another set of variables and graph them. So I don't want you guys to just do another, like just switch out Mexico for another country and do the same, I don't know, analysis where you're comparing lifespan with whatever, because that presents nothing really interesting. Or I mean, maybe there's an interesting finding there, but for part two, I want you guys to use another pair of variables, and really I've given you guys a lot of freedom for part two. So I expect everyone's part one to be quite similar to each other, because you guys are given very specific instructions. You're just graphing Mexico and the United States, and you're animating them from 1968 to like 2010 or 2012, or wherever the data goes up until. Okay, and it should animate and it should move around and whatnot. Part two, I just say create another visualization from the data from Gapminder, and so that can be any other variables. So I would like something interesting. It does not have to be animated. If you want to make an animation, that's fine. You don't have to. And I would like you to provide some kind of brief explanation about what it is that this graph or picture that is trying to portray. And so for part two, on the submission settings, I've changed it so you can allow, you can have like two files to upload, one being the image and one being an explanation. Or I know I didn't cover this, but you can look up R Markdown. Okay. And with R Markdown, you can create HTML files that incorporate image and text and whatnot. Okay. And if you're going to use R Markdown, I ask that you upload the rendered HTML file. Don't upload the raw RMD, just because the grader won't be able to view that directly without downloading it and then rendering it, which probably requires, if it's an RMD file, it probably requires access to the source files of the data, and that's going to be different on everybody's submission. So for part two, if you're going to submit an R Markdown thing, make sure you render the HTML and submit the rendered HTML. Don't submit an RMD. Or you could submit two files for part two, a GIF and a Word or a text document or something. Okay. Are there questions on this? Yes.
Is it possible to put too many like parameters in the AES part of those you plot, because night size it's not doing the population accurately?
It's not. So let's see. Okay, I will point you to a reference that might be able to answer your question, okay? So if we go to proquest.safari books online, there is a R graphics cookbook. Okay, so the web address is proquest.safari books online. We'll look up the R graphics cookbook, and if you want to mess around with the size, go to let's see, creating a balloon plot, I think is what we want to do. Let me just check and see. So we want these kinds of circles, and so the what we are doing is yeah, I guess under AES they're putting the variable in for size. So in our case, size would be equal to population, but they're adding this extra option, size underscore scale, or scale size area is you know, max size whatever, which changes the size of your circles here. Okay. So I would point to this resource. This is an excellent resource for, you know, getting started with ggplot as well. So, you know, the base documentation available on the ggplot website I think is great, but also this R graphics cookbook, which is available through Safari Books Online, which is free to you as long as you're connected to the UCLA network. Okay, so UCLA, part of your tuition goes to paying for all of these subscriptions at all of these you know, libraries, online libraries. So, you know, make use of it. Okay. Otherwise, you know, I think a private subscription is like $40 a month to Safari Books Online or something. So that's a great thing. Okay. Is this okay? Questions? Does that help kind of? Okay. So look at this. So you should be able to map a whole bunch of things into AES without too much problems, and then it's just a matter of getting it to display properly. Okay. And so here I'm doing scale size. Okay. You know, for if you want to kind of make your GIF cleaner looking, you can get rid of legends and stuff, and you would just you would turn off the legends. Removing the legend, you would just say remove the guide. Okay. The guide for fill, turn that off is basically what we're saying. So, you know, the guide for size or whatever. So all sorts of options here. Okay. Is this okay? Yes.
So if I make the animation plot in the per second, and then on the R markdown, do I have to like put the code or just explain? Because R markdown, I can see that the plot in the R markdown, the HTML plot.
So I think when you render it in R Markdown and export it as HTML, it should. It doesn't show up in the.
Just show me the result, not the graph.
It just shows you the result and not the graph. Oh, I see. Yeah, I would then. Yeah, I mean, you can submit the results separately, but also make sure you submit the graph then. Okay, and so you can. If your rendered file does not include the graph, make sure the graph is being submitted. If you're having trouble with that. Okay, we will then continue on with principal component analysis. So let me hook up. My notepad here. crazy. Got too many things on this. Okay, so we'll talk about continue talking about principal component analysis. Okay, and so just kind of just a reminder of what it is. At the heart, what we are doing, you know, the goal of PCA is to find a linear transformation of our data so that the resulting variance matrix is I guess simpler, okay? And by simpler, what we mean is that you know, just a few of the components in our variance matrix, you know, carries most of the variation. Okay, so that you know, most of the variation lies with just okay, and so, you know, we could have two-dimensional data and maybe we have something that looks like this. Okay, we've got a, you know, kind of a cloud of points. Okay, so our data y is you know, a two-dimensional y11 actually not y11, but just, okay, so we got you know, y1 and y2. Okay, so this is basically bivariate data, right? Okay, and so, you know, we could calculate something like the correlation between y1 and y2. And maybe this is 0.8 or something, okay? Who knows? Or we could look at the variance matrix. And what will our variance matrix look like? So this is, you know, the variance between y1, y2, and y1, y2, essentially. So you get ones on the diagonal, and what do you get over here? 0.8 and 0.8, right? Okay, so with principal component analysis, we're basically I'm sorry. We basically find the we do spectral decomposition of our variance matrix. Okay, so okay, and so what this basically does is we turn sigma into V lambda V transpose, okay? Lambda, the lambda matrix, is a diagonal matrix and the elements down the diagonal, these are eigenvalues, okay? So the elements down the diagonal are the eigenvalues, okay, of our matrix, of the original matrix. Okay, and then and your two, the other ones, your V and your V transpose. Okay, these are basically you take your eigenvectors. So then you got eigenvector. So V1, and then of course there's multiple elements. So and then it's just all of the eigenvectors together. Okay, so in our case, when we just have a 2x2 matrix, our diagonal matrix is just going to have dimension 2, and we're only going to have 2 eigenvectors, and that's it. Okay, and each eigenvector will only have two pieces in it, just because it's a 2x2 matrix. Pull out my other notes. So let's see if we can do this. Is this okay? So and then. Okay, so what are the eigenvalues of our correlation matrix? Okay, so so keep in mind, we got A times our eigenvector, right? This is our matrix, our square matrix, and X is our eigenvector, and this is our eigenvalue. And this is that, okay? And so effectively we can turn this into and say ax minus lambda x equals 0, okay? And we can then say a minus lambda times I. We can kind of factor this out. Lambda times the identity matrix times x equals 0, right? All right, so so we want to invert this and try to solve for this. Okay, so a minus lambda I. If so, a we will start out. We'll say is 1.8, 0.8, and 1. Okay. So So we can get, so a minus lambda I would then be 1 minus lambda, 0.8, 0.8, and 1 minus lambda. Okay, and to kind of invert this so we can solve for it, we can find the determinant of this. And what will that give us? And so what is this? This is lambda squared minus 2 lambda plus 0.36. Okay. And then so we can factor this. So, you know, what two numbers multiply to 0.36 and add up to negative 2? This is going to be lambda minus 1.8 times lambda minus 0.2. All right. And so this solution, actually, these give us our eigenvalues. So our eigenvalues will be 1.8 and 0.2. Okay. So then we can go back and try to solve for our eigenvectors. Okay, so we still have AX. So we'll try with one of our first ones. Okay, so we've got so if we say we got x1, I guess x11 and x12. This will be for eigenvalue, our first eigenvalue or eigenvector, and we'll use 1.8. Okay, so this is just solving for a system of equations. So we got x11 plus 0.8 x12 is equal to 0.8 x11 plus x12 is equal to 1.8 x11 plus 1.8 . And so if you solve for this, we end up getting x11 is equal to the negative of x12 here. Okay. If we do the same thing over here with point, okay, and then and if we plug one, oh shoot. What am I doing? Oh. Is that right? Okay. And then we can do the same thing, but with lambda equal to 0.2, and then when you solve for that one, you get x1 leads to using the other. I'm sorry, it's not right. Sorry, let me just do it this way. So using a minus lambda I times x is equal to 0. So we're going to plug in 1.8 in here or 0.2 in there. And then, so sorry, let me, this I think, this was not correct. You plug in 1.8 or plug in 0.2 into this, and when you solve these, what you get is for one vector, so your vector 1, you get that the first one is equal to the other one, the inverse of the other one, and then the other vector, you get the first one is equal, that the two components of the vectors are the same. Okay? And so, so basically, what are we supposed to do with this? Well, it's customary to make your eigenvectors unit vectors. So you would have x11, basically this squared plus you'd have the two things add up to 1, okay? So if I add these up together, then this is going to end up with x11 equal to 1. These two things, square root of 1/2, and x12 is negative square root of 1/2. Okay, and then the other one, you're going to get the same kind of thing. So x21 and x22 end up both being the square root of 1/2. So everything adds up. So our eigenvectors end up being 1 over root 2, negative 1 over root 2, and then 1 over root 2, and 1 over root 2. Okay. All right, and so this ends up being our spectral decomposition. Okay, and so we have we have our V lambda and V transpose here. Okay. And so we can verify this. You probably don't want to be doing these calculations by hand. So if we did so here I'm just creating a small data set where I know the correlation is 0.8. Okay, so here x is this, and if I do what's the correlation of x? I get this is our correlation matrix 1 and 0.8. Okay, and so I can do ask for the eigenvalues of the correlation matrix of x. Okay, and indeed this is what we get: 1.8, 0.2, and they gave me the transpose, basically. 1 over square root 2, right? 1 over square root 2 is 0.707. Okay. So let's see. So actually, it's the principal components of our correlation. So if I ask for the principal components of our correlation matrix, okay, it tells us that the loadings are basically our eigenvectors that we've used, and this will capture all of the variance in our correlation matrix here. Okay. Okay, so to just kind of as a recap of the steps that that you should take if we were to do kind of like the manual principal components of a data matrix, okay? So okay, so first you should actually center your data matrix, okay? Okay. And then you'd compute the correlation matrix. Okay. I guess it's also possible to use the covariance matrix, okay? And I guess I'll just talk about in a moment here the difference between using the correlation matrix and the covariance matrix, okay? And then, you know, perform a spectral decomposition of the correlation matrix. Okay. And your principal components then of X is X times V, where V is, you know, our eigenvector matrix, right? Matrix made up of our eigenvectors. Using the correlation matrix versus using the covariance matrix. So if we have a data set where one of the, you know, if we have a data set with, you know, several variables, right? X1, X2, X3, X4, X5, etc. Okay, and then we ask for the variance of each of these. Okay, so if the variance of X1, let's say, is 2, 3, 2, 4, and then we have 500. Okay, and we use the covariance matrix. Okay, using the covariance matrix. And then performing for principal component analysis here. Will tell us that the principal component is just X5, okay? Just because this all by itself is pretty much captures, you know, like 99% of the total variation that exists in our system here, right? So because X5 alone, you know, contributes nearly all of the variation. That exists in our system. Okay. Using using the correlation matrix, on the other hand, effectively kind of says each of these variables are equally important because now everything is on a scale from 1 to -1. Okay. In effect, standardizes our data, okay, and puts them on the same scale. All right, so let's so when we look at the loadings matrix, this tells us, kind of the linear combinations of the current variables that make up our principal components, okay? So at the end of a PCA analysis, okay, matrix, which tells us the linear combination of our current variables it's kind of like the recipes of our current variables that we should use to make our principal components. And so a lot of times, when you perform your PCA on the correlation matrix, oh wait, what am I saying? You can then use your results to kind of get back to the covariance matrix, and then you'll have the loadings. The loadings matrix tells us the linear combinations of our current variables that we use to make our principal components. So let's just kind of use a more interesting data set using our investment data. So import data set. Where did it go? Just Summary of PC and summary. Okay, so I've performed a principal component analysis on our going to those banks and saying how they recommend making investments. Okay, and we can kind of see where these it says here's component 1, component 2, and here are the loadings that they've reviewed. Okay. I can create the correlation matrix, okay? So I'll just call this R, correlation matrix of our investment data. So this kind of shows how how the data is correlated, okay? And then I can ask for the eigenvalue decomposition of our correlation matrix, okay? Did I mess something up? And so our eigenvalues and our eigenvectors in effect give us our decomposition, but let me see. I'm getting my results don't line up right now. Of course. I'm sorry. Let me see. Don't want this. Oh, okay. All right, so I'm sorry. Yeah, so what when you do the principal components directly on the principal component analysis directly on the data, it's performing the analysis on the covariance matrix, okay? And so again, there's kind of a little bit of debate on whether or not you should use the correlation matrix or covariance matrix. So you can see our loadings for component 1 says stocks is 0.706 and alternative investments is negative 6.86. If I do the eigenvalue decomposition on the covariance matrix of the investments, we can see that our first eigenvector that we have basically gives us the same results here, right? So, so the principal component analysis is essentially, you're doing your spectral decomposition, finding the eigenvalues and eigenvectors of, if you just do the data matrix directly into the principal components command, it does it on the covariance matrix of our data here, okay? And so this eigenvalue, and I'm sorry, I'm going over time here. This eigenvalue, this is the diagonal elements of that variance matrix, right? And so if I were to take the square root of this first number, okay, we're getting something a little bit different, 15.26, and it's telling me 14.97. So they should be the same. So maybe, I think what's happening a little bit is that the principal components program, when the eigenvector values are very close to 0 or small, it just drops them completely. And so I think that ends up changing the standard deviation that's being captured here. But that's what we've got. Okay, sorry for going over, and then and on next week I'll show you some neat applications of this that we can do. So.